Warpage is caused by a variation in shrinkage across a plastic molded part, and that shrinkage variation can come from several different sources. A root cause analysis from simulation can help diagnose the true cause of warpage, which can help hone in on what parameters to change for a meaningful impact on the part's dimensional stability. I'm Alex Baker, and welcome to another Moldex3D tips and tricks. In Moldex3D, we represent the warpage as a total displacement plot. This total displacement represents how far each node is moving across the geometry. For example, if I go to result and deformation, we can see that the part warps in some way, or at least it moves in some way. Each of these nodes are moving in the amount that shows up over here on the right side in the warpage scale. I can increase the scaling of this warpage to visualize that displacement a little bit better. The thing to note is that this is not purely warpage. This is a combination of material shrinkage and what we refer to as differential shrinkage, which is more commonly referred to as warpage. We can try to separate out the material shrinkage by using a mold compensation. For example, this PCABS material has a shrinkage value of 5 thousandths of an inch per inch, or 0.5%. I'm going to apply that isotropically over the entire geometry. And once I apply that, now I can see where there is truly a warpage occurring. So any of these high displacement regions are almost purely warpage. You can see that this is an out of plane displacement. This wall is kind of caving in a little bit. And so this allows us to figure out where the warpage is actually occurring. But this doesn't really help us to troubleshoot where this warpage is coming from. We can see the warpage, but we don't know where it's actually coming from. In Moldex3D, we have a way to output the different causes of warpage as individual displacement plots. To do so, we can go to the Home tab, Computation, and then under the Warp tab, we can check the output results of differential temperature and shrinkage effects. This would have to be done before you run the analysis, so if you already have your results, you will have to rerun the warpage analysis itself. You don't have to rerun the filling, packing, and cooling. You can just rerun the warpage analysis. This will give you two separate result items or two separate result sections that are called differential temperature effect and differential shrinkage effect. Our root cause analysis allows us to compare the differential temperature effect and the differential shrinkage effect to the total displacement plot to figure out which of these effects is greater. Before I break down the definitions of each of these, I'm going to show how this root cause analysis is going to work. First, I'm going to go over to the Result tab. Then I'm going to hit Compare, but I'm going to use a 3-window compare. So I'm going to click on the drop down and go to the 3-window compare. On the left side, I'll have total displacement. In the middle, I'll have differential temperature effect. And on the right side, I'm going to have differential shrinkage effect. All right, once I have all three of these compared to one another, I'm going to use sync, rotate, zoom, and pan to make sure that when I rotate or zoom in any of these windows, they all do the same thing at the same time. Now, what I'm trying to do is figure out which of these effects is comparable to the total displacement plot. The differential temperature effect shows us the effect of a variation in temperature from the core side to the cavity side of our mold or from the top to bottom side of our parts. All right, so if we have a high temperature on this side and a low temperature on this side, I could expect the part to warp towards that hotter surface. That's the differential temperature effect. The differential shrinkage effect is derived from the shrinkage variation through the core of our geometry. So the differential temperature effect is more based on what's happening on the surface level, and the differential shrinkage effect is happening more in the core or in the center of our geometry. If I have a lot of shear heating in my part, I'm going to get a large temperature differential between my gate and my end of fill, and that could cause a variation of shrinkage in the core of my part. So the reason that I have all three of these on the same window is so that I can see which of these differential temperature or differential shrinkage compares the best to the total displacement plot. And that'll tell me where a large amount of the displacement is actually coming from. In this case, the color plot for total displacement matches quite well with the total displacement plot for differential shrinkage. And you can actually see that the magnitude of differential shrinkage is greater than that of the differential temperature effect. This can tell us that the differential shrinkage effect is dominant over the differential temperature effect and is the primary cause for the warpage in this scenario. And this is great for an unfilled material, but when we have a filler, when we have an anisotropic filler in our geometry, now we have to consider the effect of fiber orientation in our warpage as well. So I'm going to switch to another run that has a fiber-filled material, and we'll do a very similar thing that requires one additional step. When you go through the computation parameters and you go to output those different effects, there is an additional one that's active for a fiber-filled material. All right, so we will output the differential temperature and shrinkage effect, but then also up above, we'll output the fiber orientation effect displacement, and that will output a couple of additional items for us to evaluate. Over in our result tree, we see that we have our total displacement, we have our differential shrinkage and temperature effects, but we also have two additional effects, which are called the fiber orientation effect and the random fiber orientation effect. We're going to break this down in two different root cause analyses. The first one is going to be to figure out if the fiber orientation effect is dominant to the total displacement. To do this, I'm going to go into a three-way compare, just like I did before. The left side, I'll have total displacement. The middle one, I'll have the fiber orientation effect. And the right one, I will have the total random fiber orientation effect. The fiber orientation effect is the displacement purely by the fiber orientation distribution throughout our geometry. Then the total random fiber orientation effect is the effect of warpage due to anisotropic shrinkage. So without the fiber orientation considered at all, our total random fiber orientation effect would tell us if the differential temperature or differential shrinkage effects are going to be more dominant than the fiber orientation effect. All right, so we can compare these two just like we did before. I'll use sync, rotate, zoom, and pan. All right, so we'll use just like we did before. We'll try to find which of these two fiber orientation effect or random fiber orientation effect compares best to the total displacement plot. And then from here, we can figure out if the differential temperature or differential shrinkage effects are dominant. All right, so we can see that the random fiber orientation effect is more aligned with the total displacement plot than the fiber orientation effect is. And so that tells me that the fiber orientation effect is not very dominant in this analysis, and the random fiber orientation effect is more dominant. And so that being said, now I'm going to break this down even a little bit further. The total random fiber orientation effect is a combination of the differential temperature effect and the differential shrinkage effect. And so I'm going to compare those three to one another now. All right, so on the left side, I'm going to put the total random fiber orientation effect. In the middle, I'm going to put the differential temperature effect. And on the right side, I'm going to put the differential shrinkage effect. Okay, and so we can see that the differential shrinkage effect is dominant to the total random fiber orientation effect, and then the random fiber orientation effect is dominant to the total displacement. So this tells me that the shrinkage throughout my core is the most dominant factor to the warpage, and I can iterate my process accordingly to impact my differential shrinkage effect, which will then trickle up all the way to the total displacement and should lower the amount of warpage and shrinkage that we get across our geometry overall. Thank you for watching this Moldex3D tips and tricks. Next week, we're going to be going over the report wizard and how to efficiently create a report output from Moldex3D. If there's a topic that you'd like to see covered in the future, you can leave a comment below. And remember to like and subscribe to the Moldex3D YouTube channel so that you get notified when new videos come out. Thanks for watching, and we'll see you in the next one.